Good afternoon. Good afternoon, and thank you for your interest in SKIM. I am Eric van Sebeel. I'm an oceanographer and SKIM user, and in this first part of the presentation, I will be explaining how SKIM will be extremely useful to better understand the transport of material floating on the surface of the ocean. But first, the summary. What is SKIM? So SKIM is going to be the first mission to directly measure the ocean's total surface current velocity, or as we abbreviate it, TSCV. It has global, regular, repeat coverage and dense sampling, and its data will allow us to estimate the surface transport as well as ocean-atmosphere exchanges to understand climate variability. It can be used to then support the management of oil and chemical spills and monitor the pathways and fate of marine plastic debris littering our ocean. So in short, SKIM would uncover how the dynamics of the ocean TSCV influence the integrated Earth system. It addresses ESA living planet challenges and serves society. But what is this total surface current velocity then? Well, the currents in the ocean vary with depth. This is a profile measured somewhere in the North Atlantic from a current meters, and it goes from almost no flow at 40 meter deep to something like 10 centimeters per second in the mixing layer. Now then, but this is not all of the flow that a water parcel actually experiences, because on top of that, there's what we call the Stokes drift. And the Stokes drift is the net drift due to the orbital motion of the waves. The two combine to form the total current profile. And it is this total current profile by which anything floating around on the ocean is moved around. And the TSCV sits right there. Now SKIM will measure the upper first meter of the ocean surface. And that can then be compared to surface drifters, to radars measuring the upper 2 meters, HF radars, I'll come back to that, and to drogue drifters that are drogued at approximately 15 meters from the operational data stream. Now, why do we care about the surface of the ocean? Because the surface of the ocean is actually where most economic activity in the ocean is taking place. It is also where most of the anthropogenic material that we put into the ocean is floating around. Think about oil, such as here from the oil spill after the Deepwater Horizon accident in 2010. Or the flotsam that was taken washed into the ocean after the 2011 Japan tsunami. Or the debris from the missing Malaysian airline MH370 flight in the Indian Ocean. In each of these cases, the first responders had real trouble trying to measure where the material would go, because they didn't have accurate total surface current velocities. SKIM will provide these. But it's not only about first-off inputs. It's also about, the TSCV also transports the plastic waste that is littering our ocean and that is causing the global plastic crisis. Now, it is instructive to see how the TSCV carries all that waste around. You may have heard of the garbage patches, the so-called islands of plastic that float around in the middle of the ocean basins. Well, here we separate out different components of the current flow to understand how that accumulation of plastic into the garbage patches happens. First off, is the geostrophic flow, which is determined from satellite altimetry and sea level anomalies. And as you see here, it actually doesn't accumulate. There's a little bit of accumulation, but that's really in the tropics, and that is really because the geostrophic balance actually breaks down there. The next up is the Ekman flow, which is the flow because of the wind stress directly on top of the ocean surface. This does accumulate, but it forms unrealistically narrow lines in each of the ocean basins. The Stokes drift, the wave orbital motion, also forms these very, very narrow lines, but they're in different locations. And actually, as you see here, quite a bit goes to Antarctica. And it's really only after we combine all of these different components that we get accumulation in the subtropical gyres, which agrees very well with what is observed. This is realistic. So SKIM will measure each of those components of the total surface current velocity, and that allows us then to understand the transport of floating material. But it's not only about anthropogenic floating material. The TSCV also carries a lot of biological material. Think about fish larvae from commercially imported species and many other organisms. One organism getting particular attention these days is sargassum. It's a seaweed that normally floats in the North Atlantic Ocean and has recently been inundating beaches all across the Caribbean, leading to serious problems to economic tourism, to the economy of tourism there, because the beaches are just too filthy to go on. Now, the picture on the left here is a paper that came out 2 weeks ago in Science, where the authors used MODIS imagery to map this sargassum from space. But knowing where the sargassum is only part of the puzzle, of course. Because policymakers and local authorities, if they want to understand when the sargassum would end up on their coastlines, then they also need to know how it is transported by ocean currents. And that is what the TSCV does. So this transport of biological material, in that transport, the Stokes drift is particularly important. And it's only very recently that we've realized that. So let me tell you a very short story about this. This is a piece of kelp, seaweed, and the story is that in 2017, a marine biologist was walking along a beach on the Antarctic Peninsula, here in the blue dot, and he spotted a piece of this kelp on the beach, and he was very surprised, because that kelp doesn't actually grow in Antarctica. It is an invasive species there. It was the first time observed, and it is related to, it's one of the causes of the marine biodiversity crisis that we're experiencing. So they analyzed this piece of kelp, and it turned out to come from South Georgia, the red dot here. And because the currents are around Antarctica, it means that it must have traveled at least 20,000 kilometers. Now that's a feat by itself. But the really special thing about it was that, according to the textbooks, this is impossible. Because the flow around Antarctica in the Southern Ocean is northward. It is away from Antarctica, and there's no way that something would actually end up on the Antarctic coast at the surface. And indeed, when we simulated this in a model where we took only the currents into account and excluded the Stokes drift, none of the virtual particles that we released in South Georgia actually came even close to Antarctica. It was really only when we added the Stokes drift that some of the particles did make it all the way to an Antarctic Peninsula. Again, showing that we need to understand, and this is in Nature Climate Change literally the first time that somebody had seen the importance of Stokes drift on this large scale, and that it did trans-basin transport, that it could affect that. Now we do have measurements of currents in the upper oceans. For example, there are not many, but an example here is this one at Station Papa, a time series of a mooring measuring the upper ocean flow. The observations are here in blue, and you see that the state-of-the-art European CMEMS model vastly underestimates its variability. And that's mainly because it doesn't get the inertial oscillations right that are there. But the geostrophic estimate derived from the satellite altimetry doesn't get any of the variability. At least it gets the mean right, though. The situation is much dire in the tropical Atlantic at the Pirata buoy. Here, the model and the observation doesn't agree at all with the observations. And the geostrophic estimate is way off on the variability. Now, we do have surface drifters also to measure the flow at the surface of the ocean. And indeed, when we recently analyzed a data set of 20,000 of those surface drifters, we found that only 40% of their velocities could be explained by either the geostrophy derived from the sea surface height or the Ekman, so the wind stress from numerical models. But if we want to explore the other almost 2/3 of the pie here, then we can't do that with drifters. And that's because 20,000 drifters sounds like a lot, but in the vast ocean, it's very, very low. This is a map of the number of samples that we get from every grid cell over the ocean. And you see that almost everywhere is not more than a handful or so of measurements. The coverage is especially poor in the tropics and in the high latitudes. but there's hope. Because, no, now it's up. Okay, so now we've reached a low point, going up. There is hope because there is a technology that can measure total surface current velocities. It's called HF radar, and it's been extremely useful around coastlines around the world. The entire US coastline is covered with it, as you see here from this map of the Oregon state here, for example. But the problem with HF radar is that it can reach out only a few hundred kilometers away from the coast. So almost all of the ocean is no data. Now, and that is the crux of SKIM. SKIM will, with its global coverage, its dense sampling, and its wide swath, really paint in this picture. And it will be our HF radar, first HF radar in space. Thank you. I will now hand over to my colleague Jamie Shutley, who will explain how the SKIM will help in understanding ocean atmosphere transport.
Thank you, Eric. So Eric has already shown this slide. So SKIM will measure the total surface current velocity within the top 1 meter of the water. And this is the velocity of the ocean as relative to the atmosphere. So the TSCV results in this interaction between the atmosphere and the ocean. And it contains the signature of the exchange between these two mediums. Currently, we rely on indicators or proxies for descriptions of this exchange, which we know are actually inadequate. We also don't know how well these proxies will perform in the future as our climate continues to warm and ocean circulation changes. This means that the different components of the SKIM measurement will enable us to unravel the importance of the wind, wave, current interactions on driving this exchange. And this capability will be further enhanced as SKIM will fly in an orbit with METOP. Now, this exchange between the ocean and the atmosphere at the interface regulates our climate and our weather. It's through continually exchanging heat, gas, and momentum. And you can see from this diagram here that all of the processes which are controlling exchange, or the majority of them, are also the ones controlling the TSCV. And in this way, the oceans have actually absorbed over 90% of all human-created heat and 25% of all human-created carbon dioxide emissions. And in the case of carbon, this carbon is also then transported away to the deep ocean and locked away from the atmosphere. So consequently, long-term weather and climate predictability has its origins in the oceans. And this is recognized in the fact that ocean surface stress, ocean heat fluxes, and surface current have all been identified by the Global Climate Observing System as essential climate variables. SKIM will actually enable, through the measurement of the TSCV, SKIM will enable us to the development of physically based descriptions of this exchange between the atmosphere and the ocean. And this will also enable us to understand the transport of carbon within the ocean and also from rivers. Annual carbon budgets are actually used by international governments, the United Nations, and the Intergovernmental Panel on Climate Change as evidence to support the reductions in carbon dioxide emissions. These assessments include emissions, which you can see in the brown and the grey on the top there, along with the natural sinks of carbon, the atmosphere, ocean, and land. Now, quantifying how much carbon dioxide goes into the ocean, their sink, is a powerful constraint on this carbon budget. Not only is it clearly needed to actually close the budget, but the estimate for the sink, the oceanic sink, is also required for estimating the land sink. And the largest uncertainty within these global calculations of the oceanic sink are due to our reliance on these proxies for describing the exchange. So SKIM will help us to reduce the uncertainty in these assessments by enabling these physically based descriptions of exchange at the atmosphere-ocean interface. So whilst the oceans have actually helped us in slowing down global warming, the absorption of carbon and heat is actually degrading their health, and it's resulting in an ocean which is becoming hot, sour, and breathless. So increasing anthropogenic emissions combined with this atmosphere-ocean exchange are actually driving this degradation. But clearly we need healthy oceans, both for food and for regulating our climate. So in 2015, the United Nations adopted the Sustainable Development Goals, and these goals and their specific timelines are targets for a blueprint to achieve a better and more sustainable future for all by 2030. And SKIM will help address 5 of these UN Sustainable Development Goals. Clearly, as I've already said, SKIM will help better quantify the state of our climate and how ocean circulation is changing, and this was in goals 13 and 14. This improved understanding will help identify ecosystems at risk, supporting goal number 14, and sustainable food production, which is captured within 12 and number 2. And in a moment, I will also explain how SKIM will in fact improve our ability to forecast rainfall, helping to address food security in equatorial regions and in support of goal number 2. And clearly, SKIM's TSCV will enable suitable locations to be identified for clean ocean energy systems for goal number 7. Therefore, SKIM is actually needed to strengthen our ability to address these sustainable development goals and to motivate action to avoid catastrophic climate change. So as I've alluded to, the TSCV is also needed for weather prediction. So the ocean is the largest thermal reservoir on Earth, and therefore long-term weather originates in the oceans. The formation of cold water in the North Atlantic, for example, is actually related to the onset of the West African monsoon that brings rainfall to the equatorial regions. And this is because wind and rainfall are closely linked to the evolution and variability of the ocean surface temperature. You can see this in this image here, for example, that the lack of information in the movement, the advection of water in the equatorial region, so this is the light purple areas, leads to differences in the equatorial heat budget, and these inaccuracies are then inherited into our weather forecasts. So this is particularly important for predicting rainfall in Africa, where populations are often reliant on agriculture and therefore vulnerable to drought. So SKIM will enable improved quantification of equatorial heat budgets, near surface advection, and therefore improve our ability to predict surface winds and rain, both over the sea and over land. So clearly there's a large number of advances that SKIM would enable for climate, weather forecasting, and our ability to monitor the health of our ocean. So as a result, within the SKIM preparatory work, we actually came up with multiple case studies that were grouped into 4 different themes, which were global ocean currents, marine debris, climate, and the fragile polar regions. These studies all covered different oceanic regions as well as the global case, so these are the areas that we've on the map here on the right, and they all focused on societal applications. So as a result of these preparatory studies, we can now say that SKIM will enable us to identify the source, fate, and degradation of marine plastics in the ocean environment, as well as identify marine protected areas which are being affected by illegal fishing from fish aggregating devices. We have also demonstrated that SKIM will enable model-based monitoring of carbon export from continental shelf seas. We have identified that SKIM will enable sub-daily measurements of ice drift and divergence and convergence of waters in polar regions, including the Southern Ocean. And as I've just mentioned, we have quantified the improvement that SKIM will make to quantifying the ocean heat budget and then the resulting impact that this has on weather forecasting. So in addition to these scientific studies, the operational organizations are now keen and interested in using SKIM. So numerical ocean forecasting models are now being used by many different countries. These were originally developed to address the need for understanding disasters at sea. So this is an example of the Prestige oil disaster. So this major disaster led to a large European-wide mobilization of HF radar and numerical modeling capabilities, as at the time they struggled to understand exactly where this oil would end up. The wave motion at the time was not well understood, so therefore it wasn't actually involved or included with any of these models, and so they really weren't able to understand where this oil would go. Whereas now, this wave motion is well understood thanks to the works of Fabrice Ardouin, Stephen Belcher, and many others, and it's now included within coupled atmospheric ocean models. And indeed, this understanding is also featured within the latest update of the European Centre for Medium Range Weather Forecasting, their model, and it's resulted in the largest performance in wave model performance in the last 20 years. And coupling of ocean and atmospheric, coupling within models for waves, sea ice, and with the atmosphere is now central to the roadmap for the Marine Copernicus service. So these modelling communities all need observations of TSCV, which SKIM would be able to provide, for actually challenging and verifying these model simulations. But this work has not come to an end. Both research and operational communities are now working on the next steps, including recent advances in atmosphere-ocean coupling. An example of this is the eddy killing effect, which is thought to describe and allow you to identify the position of the Gulf Stream. And the errors in the position of the Gulf Stream are thought to be one of the major errors in causing the reduced performance of weather forecasting in the European regions. So in future as well, the ice-free Arctic is likely to and is expected to have major implications for European and global weather. But all of these efforts lack any observations of the total surface current. And that's needed to understand how these wind, wave, and current interactions that are included in the model to actually verify these approaches and challenge these models, and SKIM will provide this. The collective needs from multiple operational communities have now led, as a result of this, to a set of requirements and goals for the observation of the TSCV. But the problem is that we don't currently have any observations of the TSCV, but SKIM would actually provide these. In addition, as you can see, the stability goal in the bottom right is actually undefined, and the reason for this is there are no data to actually define this, and again, SKIM would provide this. In 2018, we held the first Doppler from Space conference, which was attended by nearly 100 international participants. And the meeting was specifically organized to support the SKIM mission and to clarify its aims and objectives, gather user requirements, as well as developing a calibration and validation approach and strengthening US-European cooperations. And this meeting has ensured that the SKIM mission requirements are relevant to multiple scientific and user communities. SKIM now has a very strong and vibrant research and scientific community. We're in active dialogue to all the communities that I've mentioned and Eric has talked about throughout our talks, and many of them have actually actively helped shape the requirements for the SKIM mission. This wide-reaching engagement is evidenced in the large number of journal papers which are now being prepared, some of which have already been published and or are in press. And members of these communities are also using our open source toolboxes. So we have two, one for generating simulated SKIM data and a second one for using model data to calculate and understand atmospheric oceanic exchange. And indeed, we've held training workshops for both of these toolboxes. So all I'm going to say for this is that we have traced the user needs to the mission requirements, and these are all in the report for mission selection, so I won't go through these details. SKIM will uniquely observe the TSCV, and in doing so will improve our understanding of the associated atmosphere-ocean exchange. These advancements will be far-reaching for understanding climate, weather, prediction and forecasting, and the health of our oceans. And these advances are timely and needed, because they are aligned with the need to address the UN Sustainable Development Goals and the need to avoid catastrophic climate change. So I'd like to thank you for listening, and I'd now like to hand over to my colleague Fabrice Ardouin, who will explain exactly how SKIM is going to work.
Thank you. So we'll now go into the research objectives. The SKIM measurements will, research objectives. SKIM measurements will allow us to address the question, how do the dynamics of the ocean surface current influence integrated Earth system? Providing answers to that question is our main objective. And this objective is at the heart of ESA's strategy for Earth observation, and specifically the 5 Living Planet Challenges for the Ocean, or LPCOs. These 5 ranges are represented in this figure. Within the SKIM objective, we have specified 2 targets. The first target is a determination of ocean surface transport, and this is clearly related to LPCO2 on ocean circulation. And by combining currents with other measurements or estimated quantities, we can compute derived variables that are the flux or transport of plankton, plastics, and everything that drives the ocean currents. This is a clear contribution to LPCO3, which covers marine ecosystems, of which the plastic crisis is one aspect. The undersea ocean exchanges that were discussed by Jamie Shutter makes the LPCO4, but SKIM can actually do more than these 2 targets, the undersea ocean exchange and the transport. SKIM can actually also contribute to sea level because SKIM contains an Nadia altimeter, so it will contribute to coastal and regional sea level. And that's the LPCO5. And SKIM will also in many ways contribute to coastal systems. That's by providing offshore boundary conditions, among other things, for extreme sea level at the coast, and also for ocean circulation models and other studies. And we're still discovering currents in the coastal zone, and these currents are shifting with climate change, so we are really looking forward to get SKIM data for coastal applications. So that's the objective. Now, as very well expressed by Eric Van Seville, we want HF radar in space. Well, as you may know, HF radar have big antennas, and the HF waves actually don't go through the ionosphere, so that doesn't work. So we need to find something else. So we'll keep one ID from the HF radar, and that's the Doppler, because the Doppler measures directly the surface velocity. And to make it work, we'll add another very simple ID, which is a conical scanning that will going to give us a wide swath. And when you actually work out how the system works, you figure out you actually need a Nadia altimeter to be able to track the surface. So that's actually a very simple system. We have just these 3 IDs, and that's how the system is going to work. So it's so simple that you realize, well, why did we do that before? And so we didn't do it before because actually, until 20 years ago, we didn't know how the ocean surface velocities were measured by a radar. And that breakthrough only came in the last 20 years. And that missing piece of understanding is the fact that actually when we measure the velocity of the surface, it's all measured through the wave field. And so you actually need to be able to measure the waves very accurately to separate the waves and the currents. And the thing you also realize more recently is that the same velocity, the same waves that cause the Doppler signal are also the same waves that cause the Stokes drift. So you can actually have the same system to measure both the currents and the Stokes drift. Now, it would take me hours to explain to you how this Doppler wave current spectrometer, the DWACS, work. So instead, I'll use that animation. And so what you will see coming, I didn't click it right, did I? Yes. So what you see here, this globe, is actually currents from a model accelerated to have something like 1 day per second. So you can see the tides pulsing, you can see the Gulf Stream, which is this white snake here, you can see the heat going away from the equator with the currents. And actually what we get from altimeters and gravity measurements today is what you have here on the right, which is a bit more boring, less dynamic, and this is because this is only one part of the story. It's not the total surface current velocity. What we know is that the ocean surface is never at rest. It's always moving, so it doesn't have a flat surface. And you can measure the sea level using a satellite altimeter, and SKIM will actually have a nadir beam to use that technique for tracking the surface. The slope of the surface produces a pressure gradient, pushing the water, and that pressure gradient is in balance with the Coriolis force, at least at large scales and away from the equator. And that's a way to infer the surface geostrophic current, or near-surface current. But these are only 2 terms of Navier-Stokes equations, which contain many other terms, and so there's actually other forces that influence the flow, especially at small scales and at the equator. And this includes the inertial forces, the tides, and when the wind is uniform and it's steady, the wind will actually rub on the surface and push currents, and making this pattern of this Ekman spiral that was mentioned before. And of course, at small scales, the flow and the motion is dominated by ocean waves with a typical wave height, wavelengths, and directions. Now, the motion of the surface is, you can see here, the waves also actually contribute this transport, which is Stokes drift, by having the particles moving forward a little bit during the motion. And all this motion can be measured with the Doppler system. You can get a direct measurement. And so if you actually follow a facet of the ocean surface, a small rectangle, if you look at it not just vertically but obliquely, with a system that is sensitive to horizontal and vertical motion, you'll be able to actually get the horizontal velocities that project on the line of sight. The signal you measure contains two information, the backscatter power and the frequency of the signal. So if you have a lower frequency when the stuff gets back out from sea surface, you get a lower frequency shift. And if the particle is going towards you, you get a higher frequency shift, which appears here in blue in the picture. So overall, the motion of the sea surface is combined this Doppler shift, which contains both the waves and the current, as I was saying before. So it's a really combined measurement of both waves and current together in one single measurement. And so to be able to separate the two, that's where we actually need to come up with a way to measure the waves and separate this wave and current contributions. And SKIM will measure the waves as accurate as has ever been done before, thanks to a very good quality radar system. SKIM will, in practice, measure Doppler shift by the phase difference of pulses of pairs of pulses, the same thing which is used in radar meteorology. So you send two pulses and they have different phases when they hit the surface, which is due to the motion of the surface, and that phase difference gives you the motion. In reality, the footprint of the ocean contains many different velocities, so it's not just one red or blue, you get a mixture of reds and blues. All these velocities are combined. And you have to realize that in practice, our footprint is actually much, much bigger than this. The SKIM footprint is 10 kilometers in diameter, so that's typically 100 wavelengths. So even in this picture that you will see here, that's even not to scale. You have to make it like 10 times bigger than this. But it shows you, the typical modulation you get of the Doppler going over the waves. So SKIM will use vertical nadir beam. It will also use beams at 6 degrees and 12 degrees from the vertical. And these tilted beams are sensitive to horizontal motion, and that allows you to measure the surface current. For each footprint, we get a line of sight measurement. So these beams, actually there are 6 of them, and they have this pattern that will be rotating, and we flash them one by one in sequence every 200 milliseconds, and that makes this pattern on the sea surface. You have the nadir beam in white in the middle, and the spacing between the footprints is about 10 kilometers, and the swath width, which is very important, is 300 kilometers. That allows us to get this very fast revisit over the globe. Now, looking at the map of the Doppler shift on each of these footprints, you can realize that one piece of the ocean will be seen at different azimuth angle, and that allows you to combine these different look angles to get a vector, not just one component of the current. Now, to look at the waves, we have to look in more details or how the power is reflected by the sea surface. So this is an example of waves being perpendicular to the radar beam. In that case, the radar is averaged along the crest, and so you have this modulation that even when you average is remaining. If you shoot at it from the side, then when you average across the beam in the azimuth direction, then you get 0. So essentially, you get only waves in one direction, and the other direction, you don't see them anymore. And that's how the way we're going to build the full wave directional spectrum. And so the wave directional spectrum is a distribution of the wave energy as a function of frequency and direction, which is this pie chart. And each time we look at the surface at a different angle, we get one piece or two pieces in opposite directions of this wave spectrum. And by going around all the azimuths, we're able to build up the full wave directional spectrum. You can see here, the red dot in the middle is long wave swells. And on the outside, you have the short wave driven by the wind. And these are the ones very sensitive for us for the Doppler and the Stokes drift that contributes most to the Stokes drift. So in practice, SKIM is not looking straight down and shining on it. We're actually going around. And in general, the wave field is rather uniform at this scale. So we can actually combine all these measurements to make one estimation of the spectrum in a 70 by 70 kilometer box. And that's, again, our spectrum with the swell in the middle and the wind sea on the outside. And what's very important for SKIM is that we're able to resolve these relatively short waves that are super important for the Stokes drift and the wave Doppler. And I'll come back to that later. So you get this kind of pattern of the measurement across the swath. And when you actually combine the observation, we'll make measurement cells that are 30 kilometers by 30 kilometers. And on these 30 kilometer cells, we get vectors. And this is what you see. We don't have vectors in the middle because in the middle you only have one direction, which is a long track direction. So you only have one component. As SKIM flies over the globe, it will fill up the map. On average, we get a revisit of 3 days on the entire globe. And that's thanks to the white Doppler, the white swath. So that simulated current picture. And I will essentially stop the movie here. You can watch it at home if you want to see the conclusions. And we'll go straight into the next part, which is getting the requirements for the system, now that we've defined the measurement concept. So the first requirement that's really important is actually to define the orbit. And the basic way to define the orbits is just to maximize the revisit and coverage. And we want to have coverage in the Arctic because the Arctic is changing very fast. It's going to be ice-free probably in the summers by 2030. So we want to be able to observe the currents below the ice or when the ice retreats. We also define a requirement for a revisit of less than 10 days at the equator. So that's a requirement that's driving us to the width of the swath. And you can have many, many different orbits that would satisfy these requirements. And so you have to choose one. And we've chosen to fly with METOP SG-1B. And the reason is that it's an operational mission, and it carries two instruments, NWI and SKA. And they have here one animation. Oops, I don't know why it doesn't start at the beginning. Ooh, okay, try again. No. So you'll see the animation later in the talk by Egil David, but essentially the MWI is a microwave imager that will give us some measurements of the wet tropospheric corrections for the Nadia altimeter, and will also help us to flag the ice and rain. And the ocean scatterometer will help us estimate the wave Doppler and flag for the ice. And the combination of SKA and SKIM will be very interesting for other science applications, especially on the air-sea fluxes, as was mentioned by Jamie Shetler. Now, I will have to explain you for the next requirements beyond the orbits, we have to look at the SKIM measurement equation for the total surface current velocity. And basically, what we're measuring is a Doppler velocity that contains, so a geophysical Doppler velocity, UGD, that contains, as shown in the animation, the current contribution, I have here noted as UCD in blue, and the wave Doppler contribution in green. I also have to mention the non-geophysical Doppler velocity, which is this gray term here. And yeah, yes, second point, of course, sorry. Where did it work? I'll find it. Yeah. And that's actually very large because this is a velocity of the Earth measured by the radar on satellite projected on the line of sight. And so that's determined by the azimuth and incidence angle. So the knowledge of these two angles is very important to be able to get a right estimation of the non-geophysical Doppler. And this is essentially the schematic of it. So the wave velocities are typically much larger in green here than the current velocity, and the current velocity is more or less uniform. And you can think that when you do an average, the green velocities would average out because essentially they average 0. But when actually you make a measurement with the radar, you're actually measuring the normalized backscatter multiplied by the velocity, and you average it after. And the backscatter is related to the slope, and so you actually have a correlation of the slope and the velocities that gives you this very large wave Doppler in your measurement. So the question we always get when we talk to users is, what is the depth at which we measure the current? And so we already answered that, you know, it's 1 meter, but why is it 1 meter? Actually, what makes the question more interesting is that. And to get the answer of this, you have to look a bit at actually what's happening. The reason why it's 1 meter is that the ocean wave speed, and we're actually measuring everything through the ocean wave, the phase speed of the waves is modified by the current. You get a shift of the phase speed, it's just a Doppler shift of the phase speed of the ocean waves. And the ocean waves have a spectrum of slopes, and because the power that you measure with the radar is related to the slopes, essentially the speed is going to be weighted by the slope spectrum. And we had this picture in the movie, in animation, that was showing these facets as the ocean surface. So that's how people would usually think about the backscatter of the ocean. But the radar doesn't see space. The radar is only seeing time. And for radars, and some people like Bertrand Chaperon, this is actually how you understand it. You don't have to go through space. You can stay in the Fourier domain of the Doppler bandwidth, and you translate directly the frequency of the radar into the frequency of the ocean waves. And that's actually how you can actually say that directly these velocities will be, each of these velocities here, each wavelength is going to be a velocity of a given wave. Now this is what HFR does by selecting a particular wavelength. It's also what's done by the delta K processing on SKIM, but I won't talk about the delta K anymore. So I'll now walk you through how we actually process the data. So we start all from this level 2B line of sight measurement, so projected on the ground, the current velocity. We take a box of 70 by 70 kilometer in which we take all these level 2B products. And in that box, we estimate a wave spectrum. So we have it here. We also estimate the the geophysical Doppler velocity here. And we use a spectral measurement to compute first the wave Doppler, subtract the wave Doppler from the geophysical Doppler, and then we get these. So now we have, for each of these dots on this map, we have a search radius of 30 kilometers in diameter. And in that, and then we blow it up here with this, make this 30 kilometers. And for each dot, we have this line of sight velocity in blue with an uncertainty in red, and we combine this line of sight velocity to make one vector in that box of 30 by 30 kilometers. And this is our level 2C total surface current velocity. And then you do that through the entire swath, and you just essentially fill up the map with a resolution of 30 kilometers. Now, how does this data look like? So we actually have a demonstration going on now with the SWIM instrument on CFOSat. This map here on the left is showing an example of 1D wave spectra from CFOSat, the SWIM instrument, and the red colors is essentially the swell peak in the direction. This is a case of tropical cyclone Fani, which was in April off the coast of India. And you can see that this is a Copernicus Sentinel-1 image below. And basically what happened is all these 1D pieces of spectrum we do, as we've shown in animation, we get a full 2D spectrum, and that's an example of this reconstruction of the 2D spectrum. And you can actually do this processing on the entire swath, all the way right up to the coast. The difference between SWIM and SKIM is that we use a K-band radar, which gives us smaller footprint and smaller range gates, also better SNR, and then SKIM, thanks to this, can measure waves down to 30-meter wavelength. Now, I have to explain a little bit how we actually estimate the wave Doppler from these wave measurements. And it can be a bit complex, but basically we have a theory and validated by observations that gives us a forward model of how, given a wave spectrum, we have a wave Doppler. This plot here shows you the magnitude of the wave Doppler in meter per second as a function of the wind speed. And basically, we've computed millions of spectra, and all in all, they all cluster around this black line here, which is the median value. So if you had to use only one parameter to retrieve the wave Doppler, you could use the wind speed, okay? And actually, we have tested many different parameterizations using different numbers of parameters or moments of the spectrum. And this is what you get here on the right. So with only wind from NWP, you get this error on average with 40 centimeters per second, which is typically what we had as an error for Sentinel-1 processing, or sorry, MVSat, for the Doppler. And then you can use HS, the mean square slope, and the Stokes drift. And our baseline algorithm is basically using NWP wind together with the wave height, mean square slope, and Stokes drift from the wave spectra from SKIM. Now, if you have METOP SGB data together, you can reduce a little bit the error, and you can also go further by getting more information on the spectrum. Now, that algorithm was based on the assumption that we have the spectrum locally and we compute everything locally. And that works nice if things are uniform, but not uniform everywhere. In the coastal zone, that can be challenged. This picture shows you waves in the North Atlantic with open coastal waters here on the right. It's nice and uniform. And then on the coast, you see the diffraction, the very different wave fields. In this region, it's going to be a bit more difficult to combine all these wave spectra in different directions and get a 2D wave spectrum. What we know is that SKIM will get very good line-of-sight measurements on the single level 1B footprints all the way to the coast, pretty much. But in order to produce the level 2B velocities and level 2Cs, what we've done to make it simple at this phase A stage, we use a conservative approach that's just flagging everything which is less than 30 kilometers from the coast. We know that in the future we can do better. And there's a lot of areas where the total surface current velocity can be retrieved close to the coast. So I'll summarize the requirements for the system. Whoops, I shouldn't touch this. Basically, this is all based on the measurement equation. So we're measuring this V-loss. So basically, it has to be measured accurately. And we have a requirement on the precision for this. The radiometric accuracy is important for being able to retrieve the wave modulation measuring this UWD that comes into this equation. We need a wide range of azimuths to fill up the map and a wide range of incidents to fill up this swath. And so that's also important for getting this UWD term. And we also chose to use a K band and at low incidence, so it's this kind of angle, and that's because we know the physics very well in that condition, and actually Ernesto Rodriguez has shown that this is optimal. Finally, we need to know the angles of pointing very accurately, and we passed to and the mission advisory group defined this as a PSD for the angles, for the knowledge error. Other requirements are related to the nadir beam on the altimeter. Spectral resolutions, essentially we have to resolve these 30-meter wavelengths to be able to get the wave Doppler. We want to cover the Arctic because it's changing very fast, and the equator in less than 10 days, and we have to have a system that lasts long enough to see interannual variability. One issue can be flagging. So rain flagging is a known issue on K-band system, but it's actually not so much a problem. This is a simulated flag using a threshold on rain rate of 0.1 millimeter per hour. This is over 3 days, and if you actually wait long enough, the holes get filled in. And so basically, the multiple passes compensate for the data loss. Now, what we're measuring in terms of processes on the sea surface, you can look at this map of essentially time scales on the y-axis and spatial scales. And this red dot and green dot here are actually what's resolved by SKIM at high latitudes and at slightly lower latitudes. And basically, we're going to be able to resolve all these motions, most of the ocean mesoscale. We're not going to resolve the left things. And then all these things essentially correspond to this kind of level 2D product. Now, there's possibly some difficulties in retrieving fast motions that and this is an example showing you that actually fast motions can have large space and time coherence, and that's actually there's some possibility to separate these fast motions from the data. These are drifters pairs, and you can see that even if they're 100 kilometers away, they're still coherent. And so we have a way to separate this fast motion and be able to measure things like the internal tides and near inertial oscillations that are very important for ocean mixing. The SKIM validation concept is very straightforward. It's using existing operational infrastructure, essentially measuring velocities from the surface all the way to 15 meters with Argo floats, HF radars, and surface moorings, and subsurface and surface floats. And of course, SKIM will not fly alone, so there's a lot of synergy possible with other satellites. A very important aspect is that SKIM contains a nadir altimeter. It will be measuring at the same time the full wave spectrum, and so with combining this, you can actually look in much more detail at the sea state bias, which is today the largest source of error for nadir altimeters. And so that will also probably lead to reprocessing of past altimeter record and giving us a better time series of altimetry. SKIM can also help scatterometers by going from scatterometer relative wind to ocean surface wind stress, and that will demonstrate what can be done with future Doppler scatterometers. So in summary, SKIM will be the first HF radar from space. And I will just summarize what's been said in that presentation. So Eric Gansebi has explained that SKIM will be this magnific machine measuring for the first time the essential climate variable, that is a total surface current velocity, and its component Stokes drift. Jamie Shuttler has demonstrated the wide range of application of SKIM for science society. He also shown that we have a vibrant and growing user community. And I've finished by showing you how these very three simple ideas of Doppler measurement, conical scanning, giving you the Wadsworth, and nadir altimeter. All these three combined give you a new measurement concept that will be able to take us much further. So I will let you read the rest of the summary. And I would just like to thank you, all the SKIM team and all our great colleagues at ESA and the wider community that has been helping us. And I would like to say a few words about a great oceanographer and a great man who passed away this year at 101 years old. And the man who inspired many of us and the younger generations to go and explore the oceans. This man is a distinguished scientist. He was called the Einstein of the ocean. And this man is Austrian-born oceanographer Walter Munk. So Walter has a very long career starting from waves, looking at wave scattering, and all of what we do actually in the simulation that will be shown by Craig Donald in Spain is measurement in the 1950s of surface slopes. and he was a real pioneer for that. It's actually interesting that his last paper was dedicated to looking back at the very solid, a very robust relationship between slope and kinematics of a sea surface that we actually know very well, and the signature on different systems. So there was this very nice review paper about surface slopes and this sea truth. It also wrote a very interesting summary of the first 100 years of oceanography. In that summary, he had this very interesting statement that the key development between the 19th century of the Challenger and the late 20th century is adequate sampling. And by shining a wide swath on the ocean surface, SKIM and its successors will provide the adequate sampling that in this 21st century is required to explore and protect the ocean for our children, including those that have joined the School Strike for Climate. And I'll leave you the floor to the ESA System Study Manager, Eric de Wiet.
Good afternoon, everyone. My name is Eric de Wiet. After the previous talks on the groundbreaking science that SKIM will do, I will take you on a technical journey and talk about how we will implement this mission. But to start with, I would like to remind ourselves of the top 8 observation requirements that we've got from the scientist. And we start immediately with a big one. So as the first purpose-designed Doppler machine, of course, SKIM will need to measure line-of-sight velocities with very high precision. Also, we want to make sure that we coordinate lots of these different measurements into a pattern across the swath that will allow us to combine all these measurements into a map of current vectors on the surface. And this is the reason why SKIM needs this conically scanning instrument. Next up then, we have to observe in Ka band. This helps us to capture the smallest waves on the surface. It gives us narrow footprints, and also it increases the sensitivity of the pulse pair measurement technique, which I will again talk about later, although it was already explained before. Then we have to subtract our own spacecraft velocity from the velocities that we are measuring. And this depends on the projection. So for this, we need a very good pointing knowledge of our radar. Because we need this over timescales of interest, these requirements are expressed as a spectrum. But SKIM is not only about measuring velocities. It is also a very good altimeter. And our nadir altimetry requirements are on a par with those for reference altimetry missions. In order to observe currents, we need to measure waves, as was explained in the previous talk. And for that, we need good range resolution, we need good radiometric resolution, and we need good relative radiometric accuracy between the different beams. Then we need to cover all the oceans and inland seas between the latitudes of 80 degrees north and south, and we need to do so with a revisit of at least 10 days. This is what's driving our swath width, and it is also driving the total data volume that we produce. Finally, SKIM will also build up a record of ocean currents. So in order to capture signals that are relevant to climate, we need to do so for at least 5 years. We also have requirements on absolute radiometric accuracy and the radiometric stability. So we've given those requirements to 2 parallel industrial consortia, who've each come up with their own technical solution. And here we show Concept A. Concept A was designed by a consortium led by Airbus Defence and Space in Madrid and supported by the instrument provider Thales Alenia Space in Toulouse. Here we show Concept B. Here the consortium was led by OHB System in Germany, and also they were supported by the same instrument supplier, Thales Alenia Space in Toulouse. Now, the reason that both consortia were supported by the same instrument supplier, in one word, is fast track. As our director reminded us of this morning, the name of the game for Earth Explorer 9 is really to come up with a completely innovative observation concept, but relying on technologies that have already been developed or are very mature. And SKIM, the key enablers for the SKIM mission, were inherited from the missions shown here on this slide. So we're inheriting the antenna technology from a Ku-band instrument called SWIM on CFOSat, which was a joint French-Chinese mission launched in October 2018. And we are inheriting the RF electronics, the high-power amplifier, and the K-band switching electronics from the SWAT mission, which is a mission jointly developed by NASA and CNES in partnership with the Canadian Space Agency and the UK Space Agency. And it's really these investments from these ESA member states that are now enabling this new mission concept. We're also inheriting the central electronics from the Poseidon 4 central electronics unit developed for the Copernicus Sentinel-6 mission. And SKIM is taking all these technologies and combining this in a new concept, which is a coherent architecture and operates at Ka-band, which is exactly what we need in order to measure Doppler. Before we delve into the mission design, I will quickly re-explain you at the top level, the mission concept. So we have an antenna, and the function of the antenna is to conically scan a number of beams across the swath. It does this with a fixed reflector, which is not moving, but it has 6 feed horns, which are on a rotating plate. And you can see here that we have a nadir beam, shown in blue. We have 2 beams with a 6-degree incidence angle, shown in yellow and red. And then we have 3 other beams with an incidence angle of 12 degrees. And this is now rotating continuously, which results in a pattern on the surface which looks like this. You've already seen it in the video before. The rotation here is the actual rotation speed that the plate would have when we're flying in orbit. Of course, this is a bit too quickly for you to follow what's going on. So let me rewind that and do it a bit more slowly. So here you can see that we are successively firing off beams from the different feed horns, while this plate is rotating a bit more slowly this time. And once we fired off all the beams, we go back to the nadir beam. We call this firing of one beam a cycle, and the reason we call it a cycle is because it's not actually one pulse that we are sending, but it is a train of pulses that is generated, 1024 pulses. So here you can see in this animation on the right that the radar is generating one pulse, which is then switched by the duplexer to the antenna and then transmitted to ground. I repeat, this is done 1024 times in quick succession, which is shown schematically on the left. At any one time, we've got about 180 pulses in flight before we start to receive the echoes. Here you can see that the echoes are reflected from the surface as they start to make their way back up to the spacecraft. And then we are receiving them in between the time it takes to transmit 2 pulses. In fact, it is the job of the duplexer here to receive the echo and switch it to the receiving side of the radar. So this explains the sampling pattern, but it does not explain how we measure the actual velocities, which is what SKIM is all about. For that, we deploy what's called the pulse pair measurement technique, which I will explain here. So it starts by sending a pulse, which reflects from the surface. We are storing this pulse on board, and then the surface will move a little bit, and then we are quickly firing a second pulse, which we store. And now, by measuring the phase between those 2 received echoes, we have a direct measurement of the line of sight velocity. In practice, this is done by correlating 2 pulse pairs together, but that's just a way of measuring the phase. And this is quite a noisy measurement, which is why we're not doing this just once, but we're doing this for the whole cycle or burst of echoes that we've received. This is what is shown on the left here. So this processing, this averaging, this is done on board. And we have to do it on board because it would be absolutely impossible to receive all the echoes and get them all to ground while also covering the wall-to-wall all the oceans and inland seas. Now, there is a key feature that we have implemented, which was requested by the scientist, and that is to have flexibility for on the algorithms that implement this onboard processing. So therefore, and I've explained the pulse pair, which is just one stream of the onboard processing shown on this slide. But all this onboard processing is implemented in a reprogrammable chip. It's called an FPGA. So these were the, at the top level, this was the concept. So let me talk now a little bit about the mission. So the mission architecture here, you see on the left there the launcher segment. We're launching on a Vega C in a dual launch configuration. You can see the space segment at the top. Both concept A and B are based on a medium class standard platform. The sizing parameters you can find in the reference material. Our orbit is coordinated with that of METOP-SG, which allows us to ingest synergistic data from the microwave imager and the scatterometer. And then we have the ground segment, which reuses the standard Earth Explorer infrastructure from ESA with interfaces to the METOP-SG ground segment. Here you see how the swath of SKIM travels through that of the scatterometer on METOP. So we start in one swath, and then as we go over the poles, we shift to the other swath of the scatterometer. And this is achieved by applying a small rotation to the orbital plane of SKIM with respect to that of METOP. So I already explained our concept of onboard processing, which really allows us to have to cover the complete oceans and inland seas, as shown in blue here. But this is complemented by a systematic download of raw, unprocessed data. So these are the raw echoes. And this is done for a select regions of interest, shown in orange. These are regions of particular scientific interest. It corresponds roughly to 1 to 2 minutes per orbit, but you can see here that this is already responsible for nearly half of our data volume that we have to get to ground, and that's exactly why we need the onboard processing. The platform then, this is the platform for concept A. It is based on the Astrobus platform used for Ingenio SEOSAT, and also the Copernicus Sentinel-5P mission. So all the units can be accommodated on this platform, and we've done mechanical and thermal analysis to confirm the feasibility of the concept. What you can also see on the right, on the antenna, the attitude sensors are actually mounted on the radar antenna. And that is to achieve this pointing knowledge requirements that we need. So that this includes the star trackers and the fiber optic gyros. In this particular case, we also have the GNSS and the S-band antennas on the radar antenna for the best field of view. For configuration B, this is based on a modular standard platform called Nucleus, which is currently being developed as a generic product line to also support the Copernicus high-priority candidate missions. Also for this platform, the feasibility has been confirmed, and the satellite offers very comfortable design margins. Both concepts are compliant with the launcher, both in terms of volume and launch mass. You can see the two concepts in the fairing on the left. And on the right, shown schematically there, is that we have a launcher capacity into our orbit of just over 2 tons, whereas the required wet launch mass is about 1.5 tons. So we have just over 500 kilos to implement a secondary passenger mission. I will now zoom a bit more into the instrument and particularly talk a bit about the technologies being used in the instrument. Conceptually, it is an elegant, simple design. You can see here the central electronics in blue, which are then transmitting a signal via the high power amplifier in green, which then goes via the duplexer to the antenna. The signal comes back via the duplexer back to the receiving side of the central electronics. So to start with the high power amplifier, the high power amplifier consists of two units. You have the klystron, which does the amplification of the signal. The klystron is straight reuse from the SWAT program. And you can see a picture of this unit here in the middle. The large box on the left is the power supply for the klystron. And inside you have electronics, which are schematically shown on the right. This power supply will be redeveloped with European suppliers. And one particular critical item in there is what's encircled in red there. It's called a grid modulator. A grid modulator supplies a modulated high voltage to the klystron. And this is a bit challenging because of the high voltages. You really need to insulate the grid modulator. But there's also a lot of dissipation that you have to get rid of, which poses some challenges for the design. So we've started a pre-development activity on this, designed it, built a breadboard, and this is currently undergoing test, and everything is going fine. Then focusing now on the central electronics units, which integrates most of the radar functions. The central electronics units is a modular design. You can see it here on the right, and it's got 9 slices inside. Every slice is schematically shown with one color on the left. So to start with the 2 slices shown in red here, these are just power supplies, if you like. They supply secondary voltages to all the other to all the other slices. These are modified from Poseidon 4 electronics. Then we have the slice in yellow, which is the controller. It includes all the controlling software for the instrument as well. And we have the blue slice, which is the digital transmit slice, which actually generates the pulse that we are transmitting. Both of these are reused from Poseidon 4. Then we have the RF slices. These are shown also on the right. In the picture, sorry, in case you missed it, let me just show also for this one. The pictures of these slices are shown on the right. And then also here, these slices exist, and they've been implemented for the SWAT program. And we are reusing them almost without modification, with one exception, which is the low noise amplifier on the receive side. This low noise amplifier is being replaced for one that offers us a better noise figure. So this is also the subject of a pre-development activity where we have stress tested and the low noise amplifiers, 2 different kinds. And they're still in live testing. The live testing I find out today is just completed, so we have also TRL5 for this. On the receive side, we have the digital backend. Which is, the slices are also shown on the right. Again, it's a modification from Poseidon 4, but in this case, it does have a significant customization. You can see the colored squares on the right. These are ASIC chips, and we are replacing them with FPGAs, reprogrammable chips. Reprogrammable space-qualified FPGAs are now available with the similar performance as the previous generation ASICs. So this is why we can replace them and implement this onboard reprogrammable processing that I've talked about earlier. Then the ferrite assemblies, or the high power isolator, duplexer, and switch matrix. I will talk a little bit about each of these now. To start with the high power isolator. So this was also the subject of a pre-development activity. So this unit has been designed and we've run the RF simulations, and it is performing as we expect it will perform. And we will build an engineering model and test and perform testing on the engineering model. Then this is the duplexer. It's at the top there, you can see it has a number of RF switches connected by waveguides, and below you have the driving boards for these switches. The switch matrix, this is a similar technology. It's a more integrated design because it sits on the rotating part of the antenna. The switch matrix is responsible for switching the signal to the different feed horns. It is using the same technology, though. It's a number of switches with switch driver boards. Now, the switch driver boards we had to modify because we're operating with a higher switching frequency as SWAT has done. So therefore, this also gives us a higher dissipation, and therefore we had to change some components on the board. So on the left, you can see the breadboard that we've built and tested to validate our hypothesis, and everything went as expected. The antenna then is, first let's talk about the antenna structure itself. So the antenna is about 2.2 meters high, something like this, and it weighs around 80 kilograms. That includes everything on this slide, except the platform units, the star tracker and the gyros. And the man shown on the slide. This is the SWIM antenna, where we derive a lot of heritage from. It is undergoing vibration testing here. And although it is a very different antenna, because it's a Ku-band antenna, and ours is a Ka-band antenna, so it has different dimensions, we cannot underestimate the importance of the wealth of experience and know-how that we actually derive from this program, because we now know how to design, build, and test such an antenna. One aspect of the antenna where we've put in a lot of innovation is on the rotary mechanism assembly. The rotary mechanism assembly is responsible for rotating the plate with the feed horns. And here we've made some improvements. So first of all, the motor, the stepper motor, has been changed for a synchronous motor because that gives us, a lower level of micro vibrations. And then we've also inserted into the design an optical encoder to get an accurate readout of the azimuth position. And then we have replaced the slip rings, which were causing a limit on the lifetime of the mission or on the rotation speed of the mechanism. We've replaced that with roll rings, and the roll rings don't give us, in practice, any limitation. This is really important because the lifetime of a mission is not just determined by the amount of propellant you carry, it's also determined by how the lifetime that you designed for. But for this mechanism, we're not going to get any practical limitations on the SKIM lifetime. One more thing I should mention is that we have also started a pre-development activity on the RF rotary joint, which is the element that passes the RF signal from the static part to the rotating part of the antenna. Of course, we had to redesign this for Ka-band. So, I've talked about all these pre-development activities that we've started, including the grid modulator, the high-power isolator, the low-noise amplifier, the onboard processing, the switch driver, and the rotary joint. All these activities have either completed or are well on track, and Paulo, in the later talk, will talk about the status in a bit more detail. A few words on calibration and stability of the instruments. So, like any altimeter mission, we are including a GNSS reference clock, which will ensure a long-term stability. We have internal calibration loops inside the instrument that will allow us to calibrate both the transmit and receiving parts. And then also it's worth reminding that this pulse pair measurement that I explained before, it is a relative measurement, so it is inherently stable. If by any chance, and it would be unexpected, but if there is a drift on the phase of the pulse pair measurement, we would see it because we have an additional capability, which is the direct calibration loop shown on the bottom left. And this will be exercised in every cycle, so we don't have to go to a calibration mode. In every time when we are waiting, when we've transmitted the first pulses and we're waiting for the first pulses to come back, we're using this time to calibrate the electronics, so we have a self-calibrating instrument. While we're on the topic of stability, let me also spend a few words on thermoelastic distortions. So it's very important that we, as explained before, that we get a good pointing knowledge for our antenna. And that is why we've mounted the attitude sensors on the antenna. So any remaining movement that we can have must come from a thermoelastic distortion of the antenna itself. So this is caused by thermoelastic distortions of the antenna. What we show here in the top plot on the right is the off-pointing with respect to an ideal conical scan for one rotation of the rotary plate. It would do this already on ground. This in itself has nothing to do just yet with thermoelastic distortions. This is mainly caused by antenna geometry. But we have analyzed how this antenna will behave while we are on orbit. So we have calculated all the temperatures on the antenna with a 5-second time step. We've then simulated how that distorts the shape of the antenna, and then used that in RF simulations to calculate the antenna patterns to work out what the off-pointing will be. So that is good for more than 1 million antenna patterns that were calculated to obtain these little plots that you're going to see in the next couple of slides. So we can do this, as I explained, every 5 seconds, and here we're now plotting all the rotations one by one. So every line is one rotation of the conical scanner, and we've done this for an entire orbit. In this particular case, it is done for the cold orbit, and you can and the plot on the right, the lower plot on the right, is showing you the relative. It's the same data as the one on the top, but it is relative to an on-orbit mean. And what that plot tells you is that due to thermoelastic distortions, we get around plus minus 30 arc seconds of deviation in the azimuth angle. We can now do the same for the equinox orbit and the hot orbit, and we see that the long-term variation is of the same order as the variation that we would get on one single orbit. Now, what we've done is first of all, we've used this to transform it into a spectrum and to check that we are meeting our requirements. But also we have passed this time series, actually the worst one, the one on the top, the absolute azimuth deviations. We've passed this time series to the scientist, and they have used this to validate the fine pointing algorithms that Craig will talk about later. So he will pick up from where I leave this topic here. So now I would like to conclude the talk with a summary again of the requirements and how we're doing to meet those requirements. On the radial surface velocity precision, we're showing here a supplier model. The curves, the solid and the dashed curves, are for the 12 and the 6 degree beam. And as you can see, we are compliant everywhere, or maybe you cannot see it, but we are compliant everywhere. And also we are compliant on the relative radiometric accuracy within a footprint. To address the sampling of the in the SWAT, we had to come up with some kind of metric for the design purpose. And this is a simple metric that has got nothing to do with currents, but it basically calculates the uncertainty when you geometrically combine all the line of sight uncertainties into an along track and an across track component. As you can see here, of course, close to the edge of the SWAT, we don't get the along track component, and near nadir, we don't get the cross track component. But anyway, we've used this metric to optimize the sampling pattern by varying the rotation speed, the number of beams, the beam placement, etc. And then the outcome of that has been validated by the scientists to give them the performance that they need. So they have the nadir beam, they have the 6-degree and the 12-degree beams, and they have validated the azimuth diversity that they require. Then we had to observe in Ka band, which we are. And, and then we have the pointing knowledge spectral requirement, which was expressed as a mask for the broadband noise coming from the AOCS system. We're also compliant with that. And in addition, we have the peaks here. These peaks, they are caused by these periodic signals that are shown before due to the thermoelastic distortions. And these peaks are sufficiently stable for them to be removed by the fine pointing algorithms. On the nadir altimetry, we are exceeding by far the requirements, both on range precision and on range bias stability. For the wave spectrum, we are compliant on range resolution, radiometric resolution, and on the radiometric accuracy between the beams. We're covering all the oceans and inland seas between 80 degrees north and south. We have a swath width that exceeds the requirements from the scientists, and we have a mean revisit at equator that is better than what was required by the scientists. We are compliant with a minimum lifetime of 5 years, but we've sized the propellant for 7 years. On top of that, we have ample margin for further extensions if so were required, and we also don't get any limitations from our mechanisms. Thank you. We are compliant to the absolute radiometric accuracy, and we are compliant to the radiometric stability, thanks to the calibration methods that are implemented in the instrument. So, in conclusion, the mission concept is technically feasible. The observations will be co-temporal with METOP-SG 1b. We have an entirely new instrument concept. It's called a Doppler wave current scattorometer, and this instrument is implemented with proven technology. The instrument design is sound and benefits from extensive heritage. The required pointing knowledge can be achieved, and the level 1 requirements can be met. Thank you very much.